Good morning, dear students. Let me start the second part of module 2, that is signal flow graph. The contents which I'll be discussing here today is introduction to signal flow graph, definition of signal flow graph, terminology, examples, Mason's gain formula, examples of the same, signal flow graph, how to write from the block diagram, and few designs examples. Introduction. What is a signal flow graph? Signal flow graph, it is an alternate method to block diagram presentation. Okay, Samuel Jefferson Mason, who invented this procedure. Advantage of having a signal flow graph is that here we have a Mason's gain formula. We will be using that formula to get a transfer function. We don't have to do any sort of rigorous reduction technique as we have used in the block diagram. It consisting of signal flow graph consisting of nodes and connecting branches, directed connecting branches. That's all. So signal flow graph consisting of nodes and the branches which will be connecting these nodes, which has got direction also. We get to know how signals are flowing from one point to the other point, and signal relationships, interdependencies, all those things, we will easily get to know in a signal flow graph. We can write a simple signal flow graph for a given equation. So y is equal to ax. We have taken a very simple equation, and how to represent this equation in a signal flow graph. So we have taken two nodes here. Okay, one is input node and another one is the output node, because output is y and input is x. So input node I have, output node I have, and I have connected these two nodes with a branch, and this branch is having a gain a. Okay, that means by the time I reach y, I'll be having a signal which is equal to x into a. So this is a very simple representation of a given equation, which is consisting of two nodes, input node, output node, and a branch with a gain a. So in a signal flow graph, every signal is represented by a node. Okay, number of node corresponds to number of signal present in the system. Okay, and every transmission function in a signal flow graph is represented by a branch. Okay, from one node to the other node, if there is any gain or transmittance which has to be added, that is happening through branch. Okay, so we say that every transmission function in a signal flow graph is represented by a branch. Okay, branch is always unidirectional, so it has got a unique direction, which is very, very important in the analysis. And we identify the direction with an arrow. You can see here we have an arrow direction here, that is we are moving from x to y. Okay, so different models we have. In a signal flow graph, we have a different model. So here we have one model wherein which I can say that the output y1 and y2 depends on the input R1 and R2. I repeat, output y1 and y2 are dependent on the input R1 and R2. You can see the graph here. So we have taken two equations and we have represented the two equations. That means the value of y1, if I want to calculate, it depends on the input R2, G12, and input R1 into G11. So this is what the signals which contribute for the output y1. So, it is very simple. Whatever inputs we have and whatever the branch gains we have here are represented will contribute for the output. So we have one more model here. This says that the output x1 and x2 depends on input R1 and R2 as well as x1 and x2 itself. Okay, you can see here some sort of memory things involved. That is, if you are talking about an output x1 which depends on the initial values, I can say, or previous value, or it depends on the past values, we can say. So this is what we call it as another type of model, wherein which if I say x1 is equal to a11 x1 plus a12 x2, then you will find always a self loop, something like this. So this is a loop which originates from the same node and ends with the same node. Okay, that is we can have a model which is having a self what we call self loops. That is one type of models. So we have another type of models here. uh, we can say that here only one input node, only one output node exists for the graph. Okay, so rest all nodes are intermediate transmission nodes. Only two nodes are the input and output nodes. You can say that here series of nodes connection existing here. So x0 is the input node and x4 is the output node. Okay, so this is a graph where we have written based on the equation. For equation what we have here, that is x1 is equal to what? X1 is equal to a into x0 plus b into x1 plus c into x2. Okay, so we have identified here x1, x2, x3, x4 nodes. And for x1 node, how many branches are coming? How many terms? Three terms: a x0, b x1 and c x2. So x0 into a times and b naught into x1, self loop. You can see here self loop we have. And c into x2, that is from x2 through into c. I have to come to the node x1. So like that, for every node there is a equation. So number of nodes, number of equations should match. So we have four nodes, we have four equation. And anyway x0 is the input node which doesn't require any equation. Okay, so we have these x1, x2, x3, x4 number of nodes, and number of equations should match, and we have the graph for that. So this is another type of model wherein which we have one input and we have one output for the graph. Next, terminologies. We will be using few terms here with respect to signal flow graph. We have to understand that for a given signal flow graph, we will be having one node called input node. When do we call a node as an input node? An input node is a node which can take or which can give only outgoing branch. From that node, you find only outgoing branch. There will be no incoming branch. We call that branch as input node. So similarly, we have an output node. We call a node as an output node which can only sync. That means it can only receive the branches. So output node, you will find only incoming branches. Okay, such nodes are called output node. So we define here a path, a word path we define. So what is a path? It is a continuous unidirectional succession of branches along uh, along which no node is passed more than once. So this is what the definition of path we will define. That means, a continuous branch traversal you have to do it from one point to the other point. Okay, and while moving or while traversing, we should not touch any node more than once. I repeat, what is a path? Path is a traversal you are doing from one part of the graph to the other part of the graph. You are not supposed to touch a branch or a node more than once. A continuous path which you will be tracing, what we call it as a path. Okay, hope I am clear. So next we call it as a forward path. What is a forward path? Forward path is a path wherein which we start from the input node and we ends with an output node. We don't touch any branch twice. We don't touch any node twice. Okay, we should not touch a node or a branch twice. We have to travel from input node to the output node. So that is what we call it as a forward path. Okay, similarly we call it as a feedback path, or you call it we call it popularly, we call it as a feedback loop. What is a feedback loop? Feedback loop is a loop wherein which we start our traversal from a node and we travel few branches and we will come back to the same node. Okay, say for example here in the graph x2 node. So I'll start my traversal from x2. I take a branch a32 and I'll be moving to x3, and I'll coming back to x2 through the branch a23. I'll be reaching my x2 node back. So what I did, I'll start my journey from a node and I do from traversal. I'll travel in the graph and I'll be coming back to the same node. So that's what we call it as a loop. We call that as a closed path or a loop. Okay, so So next is what is a self loop? So self loop is one. Self loop is one in which we you find a branch. It consisting of a branch which originate from a node and ends in the same node. I repeat, self loop is only one single branch which originate from a node and ends in the same node. In the graph, you can see a branch A33. It originates from the node X3 and ends in the same node X3. Okay, X3 is a node. You will find a branch A33 originate and ends in the same node. Okay, what is the gain of a branch or a transmission, we call it as? So gain of a branch is, the whatever value we write in the branch is what we call it as a gain or a transmission of the branch. That means while signal traversing through that branch, it will get the gain of that particular value. Say for example, I am starting from x1, a signal is originating from x1 and it is traveling in this branch and it is reaching x2. What we can say, the signal x1 got multiplied by a21. In other words, signal got the gain of a21 because it has traveled that particular branch. Okay, this is what we call it as the branch transmission, or we call it as a branch gain. Similarly, we can have a path gain. What is a path gain? Path gain, we say that whenever you do, whenever you do a path traversal, whatever gain we encounter, we call it as a path gain. Say for example, I have a path. I have a path here. Say from x1 to x2, x3, x4. I have traveled. Say for example, from x1 to x4, I have moved in this fashion. I have crossed a21, a32, a43. Then I can say that that particular path gain is a21 multiplied by a32 multiplied by a43. So I have to now compute the cumulative product of all the three branches, because I have traveled in through those branches. So that is what we call it as a path gain. That is whatever the gain you encounter in tracing that particular path, we call it as a path gain. Similarly, we can have a loop gain. So identify any loop for that matter. So whatever the branch traversal you do, those branch gains, if you compute product, if you compute, it's a loop gain. Say for example, here we have a loop, that is I'll be starting from a node x2 through a2, a32, I'll be going to node 3, and through a23 I'll be coming back to the node x2. Say for example, this is a loop, right? So what is the loop gain? It is a32 into a23. How can I say that? So while tracing this particular loop, I will be crossing, or I'll be traveling through these two branch. I have to take the product of these branch gain, and that is what I'll be getting loop gain. Okay, so that is what we call it as a loop gain. Okay, so we identify non-touching loops. So how can we say two loops are non-touching? So you can identify two loops here. This is one loop, that is x2, x3 is one loop, and at x3 you have another loop. So like that, in few graphs you may find more than two loops existing. So we define any two loops as non-touching if they are not sharing any nodes or branch in common. I repeat, any two loops are called non-touching if they are not sharing any nodes or a branch in common. So if I take this graph as an example, I have one loop here and I have another loop here. They are non, I cannot say that they are non-touching. Why? Because x3 node is common for both the loops. X3 node is common for both the loop. So we don't consider that to be, we don't consider those two loops as a non-touching loops. Okay, so that is about the terminologies which we will be using. So now we will see the signal flow graph. I'll take an example signal flow graph, and let us identify few parameters which we have listed here. So for the given signal flow graph, I'm trying to identify what is input node, what is output node, forward path, how many forward paths are there, how many loops are there, or you can call it as feedback path. In few literature, they have given feedback path, and in few literature, or popularly we call it as feedback loops. And determination of loop gains of feedback loops, determination of path gains, and identifying the non-touching loops. So all these things we are doing, some analysis we are doing for the given signal flow graph. So signal flow graph is very clear here. We have to identify the following. Which is an input node? Input node is a node which can have only outgoing branch. That's what the definition we have seen. So in this graph, we have RFS, a node is an input node. Why do I call it as an input node? Because only output branch we have. That is only outgoing branch we have. Similarly, CFS is an output node. How do I call this as an output node? Because according to the definition we have seen in the previous slide, we found that output node contains only incoming branch. Okay, only incoming branch we have. So this is a output node. Okay, now I have to trace the forward path. That is what the section C we have. So how to identify the forward path? So to identify the forward path, what I have to do is I have to start my journey from input node, and I have to reach the output node, and I have to see in how many ways I can reach the output node from the input node. So all the possible path I have to identify. So that gives me the number of forward path which this signal flow graph has got. Okay, so I can give the count. So how many ways I can reach from left node to the right node here? That is a input node to the output node. So we have one straight path here. We can have this straight path, and another one is till here, that is G1, G2, G3, G4 I'll travel, and instead of G5 I can take a G6 path, and through G7 I can go to CS, that is output node. So I have two possible forward path. I repeat once again, what is a forward path? It is the traversal from input node to the output node. You have to travel from input node to the output node. Okay, and in how many ways you can reach this output node from the input node is what we call it as the number of forward path. Okay, so we have only two paths. I can travel like this: G1, G2, G3, G4, G5 and G7, and another way is G1, G2, G3, G4, G6, G7. Okay, so only two forward path I have. What are the other branches here? They are having in the other direction. While tracing the path, you have to take care your branch direction should match with the direction of your movement, or the signal movement here we are talking about. So if they are not matching, you cannot trace the path. We can't call them as a path. Okay, so this is about the different forward path. Okay, so as I said, there is two forward path. The first path we have identified. So okay, the red line you can see G1, G2, G3, G4, G5, G7. That is one forward path I have identified, and the path gain I have mentioned. Okay, next, what is that blue line we have? So G1, G2, G3, G4 and G6, G7. That is the another forward path. Okay, now, how many loops are there in the graph we have to identify? Okay, as we have seen the definition of a loop, I have to start from a node. I can travel few branches and I should come back to the same node. Okay, so I'll start from this node. Okay, it is visible, it is visible. So we have to identify such particular loop. So I will start from this node. I'll go through G2 branch. I'll take H1 branch and I'll come back to the same node. Okay, so this is what I call it as one loop. Okay, so similarly I can start from this node. Okay, I can start from this node. I can take a G4 branch and H2, G4 H2, that is another loop. Similarly, I can take G4, G5, okay, and H3, correct, another loop, correct, and I can take G4, G6, H3, another loop. So totally there are 4 loops. Okay, hope the 4 loops you have found out. The loop 1 is this. Okay, loop 1 is this, that is G2 and H1. That is one loop, clearly visible. Okay, another loop is G4 and H2. G4 and H2 is the another loop. And we have a third loop, yellow colored. third loop. Okay, that is G4, G5 and H3. Okay, and we have a fourth loop. Hope that pink you can follow, G4, G6 and H3. That is the fourth loop we have identified along with the path gain. Okay, so now I have to identify how many two non-touching loops which are existing in the graph. Okay, I repeat, I have to identify two non-touching loops here. Okay, so you can easily say that here loop 1. Okay, it is loop 1 and loop 2. This is what we have named as loop 2 and this is what we named it as loop 1. They are not touching each other. You can clearly visualize they are not touching each other because the branch and the node for this loop is totally different from the branch and the nodes of this particular loop. So we say that they are non-touching. Okay, so similarly I can say that this particular loop and this particular loop is non-touching. That is loop 1 and loop 3 are non-touching. Similarly loop 1 and loop 4 is non-touching. Loop 4 is this which we have identified. Loop 4 is non-touching. So that's what we have listed here. There are 3 pairs of non-touching loops. Okay, there are 3 pairs of non-touching loops which we have in this graph. Okay, so similarly if I try to identify is there any 3 non-touching loop existing, then we say no, there is no 3 individual loops which are non-touching to each other. That doesn't exist in this particular graph. So only this much we have. Okay, so next problem. So hope we have completed all the parameter which we are supposed to calculate. Okay, so what we are supposed to calculate here, so we have to calculate input node, output node, forward path. We have done it. Number of loops we have done it. We have determined the loop gains, we have determined the path gain, and we have identified non-touching loops also. So all the parameter for this graph we have completed. So we are going to the next graph. Okay, next graph we are going now. So what we have to do is here same procedure we have to repeat. Input node identification, output node, number of forward path identification, number of loop identification. Is there any self loop? You have to check, and you have to determine the loop gains of the feedback loops, and you have to determine the forward path gain. Okay, the same parameter we are repeating for this particular example. Okay, so X1 we have here, which we call it as input node, and X8 we have here, we call it as an output node. Why? Because according to the definition as we have seen, X1 is the input node because it has got only outgoing branch. X8 is the output node because it has got only incoming branch. Okay, that is over. AB is over. So forward path, in how many ways I can reach from X1 to X8? So one is the straight direct path. Okay, and another one is the A72 path. We can take it and we can reach it. So we have totally 2 forward path. Okay, we have totally sorry, the 3 forward path I have missed here. So one more path we have, that is the third forward path. Okay, so I repeat here how many forward path. Please try to identify the first forward path. Okay, the red color line, that is X1, X2, X3, X4, X5, X6, X7, X8 node we can travel. That is one forward path. And another one is the blue color line which we have taken here. That is why X1, X2, X7, X8, and lastly this X1, X2, X4, X5, X6, X7, X8. Okay, totally 3 forward path we have. Now how many loops are there? Okay, how many loops are there? It is totally 10 loops. Okay, 10 loops we have. That is the first loop. This is first loop, and this is second loop, this is third loop, and fourth one, fifth one, and this is sixth one. Okay, so totally here we have identified 6 loops. Okay, and seventh one we have here. See here, this is one loop. I call it as 7th loop. Okay, this is 7th loop. Okay, and this is 8th loop. Can you identify this 8th loop? That is A65, A76, and A57. Okay, 8th loop. Okay, and ninth one, this red color you can see, this is 9th one. Okay, and this is the 10th one. Okay, so this is the 10th loop we have. Okay, it is clearly visible, you know, you can clearly distinguish this is what we call, this is 10th loop of the graph. Okay, so and we have one self loop. Okay, what is this? We have one self loop. This has been asked here, that is part E, how many self loops? So only one self loop. What is a self loop? It originates from a node and ends in the same node. Okay, so one self node is existing. So now we are going to give all the loops which we have identified, and its gains we are giving here. Okay, so how to calculate the gain? As we have seen the loop 1, which is having A3 to A3 to A23. Okay, so like that, all the loops which we have identified, all the 10 loops which we have identified, whose path gain, or what we call, whose loop gain we have mentioned here. Okay, loop gain we have mentioned. Now the forward path gain. So that is section G. What is that? It is a path gain calculation, forward path gain calculation. We have to do it. We have traced 3 different paths, correct? So while tracing those paths, whatever gain we encounter, that's what we have to compute here. So first path gain is the straight path which we have identified. So I have A32, A43, A54, A65, A76, and this is unity. Okay, and the other path is this A72, a single A72, and anyway this is unity and this is unity. Okay, what is the other path? We have other path here, that is A42, A54, A65, A76, and 1. Okay, so we have given here the section 8 you know, the what we call path gains we have computed. Okay, I'll stop here. I'll continue with this in the next class. Thank you.